To the pledge. Let's go ahead and stand for the pledge, please. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Thank you. Have a most awesome, fun-filled day today. Please remember to be responsible and respectful to all those around you. Adios.
Adios. All right. Okay. Your default has changed to, yeah, whatever. Great. Whoa. That's not even close. Okay, cool. Here we go. All right, close your Chromebooks and your turn to put your phones down below. Put all your food and your drinks down below. Blah, 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 as always, every day. Okay, here's the deal. I will give you plenty of time to work today, okay? But I also need to go over constructions. How many of you have watched your construction videos already? Good deal. Okay, now, let's talk a little bit about constructions. With that, I'm going to pull up docs and a blank one. Now, normally, if this were a normal year, we would definitely be doing full-on construction videos. However, because we are not in a normal year, I just don't think it's absolutely necessary to spend the time in class for really large tongues. Yeah, it's a tongue depressor, but it's huge. I don't know, it's just what I found a minute ago. All right. I am going to show you a couple things, because if you go back to the very first things we did in this class, it was talking about Euclid and the history of math, correct? And everything was based in geometry off of the world around them. And so you didn't start with rulers, protractors, and compasses. You started with something as simple as this, something that is nothing more than a straight edge, okay? Cool. There's a lot of people that are super interested in this part of their desk right there. All right, so with that, we need to know, how do we start with basic geometry? Well, obviously the most basic thing is a point. But if I have a segment, something like this, I want to be able to copy that segment. Well, in this case, I can use something that is just long enough to say, if I have this segment, how long do I do it? Well, I simply figure out how long this is using a piece of string, a piece of wood, etc. And I match it here, cross out that. If this is A, this is B, this is A prime and B prime. Why do I use the little apostrophes there? Why did I say A prime and B prime? What does this indicate? What do the little dots indicate here? If I did, it's the second version of it, right? So here's the original, here's the copy. It tells you which one's original, which one's a copy. Now, if I had something like the following, here's an angle, and I want to copy that angle. Well, I could totally copy that angle. We'll start with a new baseline, and we'll start right here, and we mark it. Wow, that's a mess. Never done this on the little touch panel thing before. Okay. So by using just a straight edge, something that I can latch onto, I can measure directly where it needs to go. And once I have that, I simply go through the point, and if this was 32 degrees, then this should be 32 degrees. Well, here's the thing. In geometry, if I can say, however long this is, I can make this just as long. However big this angle is, I can make this angle just as big. Can I now copy every figure I can make? So in this case, we have angle A, B, C. And here we have angle A prime, B prime, C prime. That's our copy. Now, give me another geometric shape. Give me any geometric shape you can think of.
There's a rectangle word.
A rectangle. Okay, what's a rectangle? What does it need?
4 sides.
4 sides. Okay. Well, I don't know about 4 sides, but I got one side here. Can I make one straight side? What do I need to do to make that into a rectangle? I need 3 more sides, but those 3 sides are very specific.
2 of them need to be like shorter, but also parallel.
Okay, the other 2 sides have to be parallel. They could either be shorter, probably because of the way I drew my line. But I mean, if I needed to, if I went the other way, it could be longer. But yeah, not the same size, but parallel. And what else?
1 parallel.
1 parallel to this line. So let's start by getting a line parallel here. Here's the problem. I could guesstimate, but could I be like a little high or a little low? If I just like that, there's no guarantee, is there? What we need is we need a way to truly get parallel. And to do that, what I can do is I can make an arc from this end, and we'll just make a point right here, and an arc from this end. Now, because I use the same length from both places, what I've really kind of done is made an isosceles triangle. But you'll notice I have a point here and a point here. If I draw, oh boy, that's bad. If I draw through that, what did I just create? A line that is perpendicular. So that's 90, you say, but I thought we wanted parallel. Well, we do, but I got to go perpendicular first. And here's why. Because if I go, whoa, that's bad. I don't really have any compasses or straight edges I can use on an active panel, and I have never used it before. There we go. Now if I connect here and here, what angle do I have here? 90. Here's 90, correct? 90, 90, 90, 90, 90. What is guaranteed now to be true about those 2 red lines? They have to be parallel, because is this angle 90 and this angle 90? Those are what kind of angles? The other one. Not alternate interior, not alternate exterior, but corresponding. Now, by the way, since it makes 4 90-degree angles, could I go alternate interior? But those are guaranteed parallel, aren't they? Well, how do I make a rectangle? How do I make a rectangle? I need to add another side, and to do that, could I come over here and create a perpendicular over here?
There's a lot of words for this.
I agree with you.
You need to do this every so time we draw a shape now.
No. But your disdain is palpable. Now, in this case, do I get another 90-degree angle here? And so what's true about these 2 lines? Blue line and green line are now, because corresponding or alternate interior or whichever one you want, because it makes 4 right angles, right? Do I need to do it again here? How come I don't need to do it here? Ah, very good. If I have this one and I know the 2 red lines are parallel, can I say corresponding angles are congruent? So automatically, do I have 4 90s? Do I now have 2 shorter sides and 2 longer sides? Whew. Now, let's go back to Massey's point. Is that a lot of work? Yes, it is a lot of work. But here's the thing. Why am I not having you do all these this year? Because it takes a lot of class time, right? Yes.
I have a question.
Yes.
Why can't you just use a ruler and measure every side and make it even?
Okay. Now, let's go back and let's take this in 2 parts. Number 1, we don't have a tool that is marked. Okay, you'll notice this is nothing but a straight edge. Second thing is, let's assume you did a ruler, right? And you said, all right, I want something that is totally the same length, right? And totally same length, right? Is that a rectangle? Wow.
I was saying you could do like 5 on the long side and 3 on the short side.
Sure, I could. Yeah, I can make them different lengths. But here's the problem. Remember, a rectangle is not just the different, it's not just the different lengths of sides, right? What has to be true for it to be a true rectangle? 90-degree angles. Is there anything about me measuring that guarantees that it's a 90-degree angle? Get my drift? Could technically, if I exaggerated this, could I have made that shape there? Like, could the green shape really be one of those, just only a little bit? What shape is that? Assuming it's parallel, because again, did I just estimate those parallel? Versus up here, I can show you by my swoops that it's correctly parallel, right? So this is a good representation. This can be proven. Does that make sense? That's why. By the way, how would I guarantee make one of these? Instead of making perpendiculars to make rectangles, how would I make something like a parallelogram where it's at an angle? Well, what 2 skills did I start our day with? Copy a segment, and we copied angles, didn't we? So, here we go. Let's make a parallelogram out of this length and this length. Okay? How do I make this into a parallelogram? Copy the angle. So here we go. You'll notice I didn't change my finger, did I? And then how do we copy the angle? We say it's from here to here. There we go. Now, can I say those angles are congruent? Is that true? How do I make sure I land at the right spot? Because I may start drawing here. How do I know where to draw to? Well, what was the other skill we started our morning with? Copy a segment. So can I do this? Right there. And would that guarantee it now? Now, how do I know this line and this line are parallel? Okay, I know this line and or this angle and this angle are the same angles. So these 2 lines are parallel, correct? And then did we make sure these were congruent, like you just said a second ago? So if they are parallel and congruent, then here to here has to be parallel and congruent. Okay? Now, do you see why constructions and proofs go hand in hand? Because you have to be able to use basically three different things. Copy a segment, copy an angle, and perpendicular bisector. Those three things, along with all the properties, allow you to make almost all of the shapes. What shape isn't represented up here? Circle. How in the world do I make a circle with a straight edge? Oh, it's actually the easiest one to do, isn't it? Well, okay, it's the easiest one to understand. It's going to be the absolute hardest one to actually do with this stick. All right, here we go. You ready? My first attempt is not great. All right.
You're like 3/4 done.
There. Look at that. Okay. Why is actually the circle the easiest construction in the world? Because the definition of a circle is all points the same distance from a point. Or, short version, all radii are equal. All radii, radius. Plural would be radii. I don't see anything at all weird about this word with two I's at the end. Yeah. Okay. All radii are equal, so it works out. Okay. So we have circles, we have rectangles, we have parallelograms. We could do triangles, right? Because what if I wanted an isosceles triangle? How would I draw an isosceles triangle? Start with a line. So I'm going to make one angle over here, right? What? I think we should know isosceles at this point. Do I have an angle down here? What's true about an isosceles triangle? The two bottom angles have to be congruent, correct? So here we go. And what are you trying to say? All right. Could I just copy this angle on the other side? That's because you're not even sitting in the right seat. So, did I copy that angle correctly? I hope so, ideally. Which means if the two base angles are the same, what's true about the sides? They're the same. How do you know this? Is that one of our properties? Now, let's see how good I am at constructions. Because that's actually pretty good, isn't it? Here we go. That's how long this is. That's how long that is. That's not bad. So it is actually pretty isosceles. What is the hard problem, though, of all constructions? It's only as good as me. It's only as good as the artist, right? What if clearly there's a little wiggling going on up here, right? It's not like super exact. It's because we have good methods, but it's still only as good as the artist or his tools. Okay, so those basic three, copy a segment, copy an angle, and perpendicular bisector, are all that makes all of the Euclidean shapes in the Euclidean universe. okay? By the way, just for fun, how do I make an octagon? 8 sides. How do I make a regular octagon? What's a regular figure mean? All the sides and all the angles are congruent, right? We already made a rectangle with construction, so I won't waste your time. Can I make a square with constructions?
Yes.
Make 90s, make parallels, da 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 da. Remember, when we make a perpendicular bisector, it not only makes a line that is perpendicular, it also finds a midpoint and cuts the two sides in half, okay? What I could do is I could find the perpendicular bisector of this and find the midpoint here, and the midpoint here, and the midpoint here, and the midpoint here, and the midpoint. So midpoint, then midpoint, 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 midpoint. Could I cut each side into 4 equal parts by doing in half and then in half again? And then connect them up. Okay? All of this can be done with construction. I'm not spending my time in class having you do all of them because we don't have time this year. But I want you to be able to see them. I also want you to understand by the time you get down here, look at how some of the craziness that you can create with just the same basic copy a segment, copy an angle, perpendicular bisector. All of that goes together. It's also going to be important because as soon as we finish this chapter, we go into a chapter on polygons, where we're going to be doing a lot because there's only 2 slides of it thus far. Not even close. That's literally the first lesson. So then we're going to go into polygons, and because once you can build on it, then you can build absolutely every shape that we have using the polygon family tree, all the way up to undecagons and dodecagons. So lots of fun. That's where we're headed next. All right, with that in mind, you already have homework. Your test, there is no time limit, I guess, on this test because I'm very special. So that means you could start it today in class and finish it some other time later today, if you wish. Okay? So your job is to basically get this. If you want to, you can finish this and not have any homework for the weekend. So get after it.